Standard data center observability stacks focus on the software layer, tracking application performance, Kubernetes orchestration, and operating system health. But this visibility requires a running operating system. If a kernel panic occurs or a host hangs, that server suddenly drops off the primary network. While your dashboard shows a dead node, the physical machine is still active, drawing power, spinning fans, and generating heat in the dark. This secondary pathway is the Baseboard Management Controller, or BMC, telemetry layer. The BMC is a dedicated processor on the motherboard that operates entirely out of band on a separate management network. It draws standby power even when the host is powered down. This allows for the continuous tracking of physical metrics, fan speeds, voltages, thermal states, and memory health. OS-dependent agents are completely blind to this layer. They cannot see pre-boot hardware errors or the events that follow a total system shutdown. Relying solely on software-level agents creates a massive operational blind spot. True full-stack visibility requires the integration of out-of-band hardware telemetry. To understand where this data lives, we look first at the macro level. The Building Management System, or BMS, tracks the facility infrastructure. While the BMS monitors the room's cooling and power arrays, it cannot see inside the individual server chassis. Above the physical hardware sits the software layer, where standard observability platforms operate. This layer handles Kubernetes orchestration and application process metrics, but it is disconnected from the physical silicon. Between the facility and the software is the missing physical layer. This is the 20% gap where the BMC resides. Operators often conflate the BMS with the BMC, assuming facility-level monitoring covers the servers. In reality, they are distinct systems, monitoring different layers. Pulling basic health flags into an OS-based platform through custom forwarders is a common but insufficient workaround. It lacks the dense time series data needed for predictive analysis. The BMC serves as the mandatory complementary foundation, sitting squarely between the building's infrastructure and the application stack. This gap is becoming a critical failure point as AI workloads push hardware to its physical limits. Modern AI-optimized servers draw 10 times more power than prior generations, pushing rack density toward the 50 to 100 kilowatt range. At these densities, minor thermal anomalies quickly escalate into critical threats to the hardware. This chart shows fan curve drift, a subtle early warning signal of hardware stress. Over several weeks, the fan RPM increases steadily. While the fan speed climbs, the blue line representing the CPU thermal margin remains horizontal. The server is working significantly harder to maintain the same temperature envelope, a clear sign of impending mechanical or thermal failure. An OS-level agent only sees the stable CPU temperature and reports that the system is healthy. Only the out-of-band BMC has the resolution required to track these specific inlet gradients and fan curves. In high-density AI environments, detecting these slow burn signals via the BMC is the only way to prevent catastrophic thermal cascades. Beyond physical uptime, hardware telemetry is now a matter of legal compliance. The EU Energy Efficiency Directive, or EED, mandates annual reporting for any data center exceeding 500 kilowatts. This document illustrates the required reporting on server utilization and IT equipment efficiency. Facility-level BMS data only captures about 80% of the information needed for an EED audit. The missing 20%, detailed input and output power per supply and voltage drift, resides exclusively in the BMC. BMC telemetry has evolved into a mandatory legal compliance layer for operating high-density facilities in 2026. Technically, modern BMC monitoring has moved far beyond legacy IPMI protocols. While IPMI remains a baseline, this narrow pipe is insufficient for the high-volume time series data modern clusters generate. The industry standard is now Redfish, a RESTful API capable of moving massive telemetry streams across multi-vendor fleets. Deep diagnostics often require supplemental vendor-native interfaces, such as Dell's iDRAC, HPE's ILO, Huawei's IBMC, or Lenovo's xClarity. While connecting to a single server is a trivial networking task, the primary architectural challenge lies in building a data plane that can normalize these diverse pipelines into a single standard. The challenge of data normalization becomes apparent when scaling to a 4,000-node cluster. A deployment of this size generates millions of individual sensor readings every minute across various protocols. At this scale, raw telemetry is purely noise. Human operators cannot manually identify the patterns that precede a hardware failure. To derive value, we must layer AI predictive models over the multi-vendor hardware data. These models translate raw sensor patterns into specific operational recommendations. Platforms like Sensaka DCOS ingest this multi-vendor data to automate predictive maintenance and generate precise efficiency reporting. We have seen how the BMC fills the blind spot left by the OS, manages the physics of high-density AI, and meets the demands of regulatory compliance. In the modern data center, true operational resilience and full-stack observability begin deep inside the out-of-band silicon.